I'm the dummy. So y and b are both 1, right?
Yeah.
So that's 1. But every, let's see here, xa, that's 0, xb, 0, ya, 0. Right. Mm-hmm.
That's 1, and then y 0.
So what's going on here is that, 1, 0, which, we would sometimes call E1, right?
Mm-hmm.
This is serving as the number 1 in this number system. Or if you want me to go back to my sort of initial notation, it's really 1 for this number system we're looking at. In contrast, but I'm just going to call that 1 for the sake of brevity. And 0, 1, on the other hand, is E2, but we call this thing J in this system. And this equation is just another way of saying J times J, which we'll denote as J squared, is 1. In contrast, if you go through the same notational hullabaloo for the complex number system, you'd see that 0, 1 times 0, 1 is minus 1, 0, which is to say that I squared is minus 1. But the larger point here is that we can define a multiplication on R2 by this definition right here, and you can check that that is associative, bilinear, it satisfies the axioms for an algebra. So this makes R2 paired with this multiplication right here an algebra.
So how are you getting so x with a in the upright column?
Mm-hmm.
Well, no, start from what you already have. So x and a, x times a, you're saying.
Oh, I'm saying, my basically man behind the curtain is that x, y, we think of as x plus jy. And a comma b here is a plus bj, using the 1 in j notation to cover up the vector nature of what's going on here. And then really we're just multiplying x plus jy times a plus bj, subject to the everything works like normal.
Oh, so y plus, and that'd be by would be 1.
Yeah, so exact by j squared. J squared is 1, so we just get by. And then j gives me an xb, rather.
Yeah, xbj and yaj.
Yeah, y. I'm trying to keep the letters the same just for the sake of just pattern matching, but that is what I had up here, and this is what I had up here.
Okay, and then for the little coordinate system, why is xa 1?
Why is
because
x?
Wouldn't just the j term have a j?
Which one are we? Are we talking about this equation or that this equation?
One, yeah.
Oh, well, y is 0 and b is 0, so yb is 0.
Y is 0 and b is 0 on the top row.
So this one here?
Okay, I see.
That's.
And then on the bottom one it'd be 1, 0 because.
Yeah.
No, but okay. X and A are 1, 0, 0, and then for the bottom one, wouldn't it be 0, 1?
No, it's 1, 0, because it's j squared is 1. 1, 0 serves as the number 1 here for the algebra.
I'm sorry, what am I not getting? Then you multiplied it out. So this little coordinate system that kind of looks like a matrix, the 1, 0, 1, 0, 0, 1, 0, 1. X and A are 1. That equals 1. But
Yep.
Y and B are 0 according to that top row. So when we're the top column. So when we go to the second column, X and A are now 0.
Yep.
And Y and B are now 1.
Yep.
So, but why'd you flip it? Like the coordinate.
Why did I flip it? Oh, because this here, what I'm showing here is that 1 times 1 is 1, but this equation here shows that j times j is also 1. That's all I'm trying to. What I'm trying to say is that. Okay, so one of the criticisms of this whole world of algebra is like, well, that doesn't even make sense. Well, how can j times j be 1 and j not be 1 or minus 1? Well, it is not 1 or minus 1. It is something else. Like minus 1 here is minus 1, 0, right?
Yeah.
And that is not equal to 0, 1, which is our j, right? So this number system, it has something much more interesting happening with quadratic equations than we're used to.
Yeah, I can see that now. It's the same thing happens in complex numbers too, like with the negative 1 squared.
But with the complex numbers, the quadratic is pretty well behaved. Like
Yeah, I know, but like it's still not the same because you get negative ones and stuff.
Very true. It is different. So this number system I'm talking about here, and I haven't called it yet, but I call this the hyperbolic numbers. And there are other names for it, but sometimes people call them the Lorentz numbers because of their connection with special relativity and such, but I have been calling them hyperbolic numbers. I'm going to continue calling them hyperbolic numbers, and you'll see why. There are also some other people have a lot more to say about, I'm trying to remember, I guess, Cayley algebras, or I'm going to,
Get all this done.
oh, okay. So, natural question to ask is, what's the regular representation of the hyperbolic numbers look like, right? So we can figure that out pretty quickly. Regular representation to hyperbolic numbers should be matrices of the form a plus bj, comma, a plus bj times j, right? What's that look like? Well, we've got a plus bj, and this multiplies what? Aj plus bj squared, which is just b again, right? So what you got? You got a, b, b, a. So there you go. That is the regular representation of the hyperbolic numbers. Excuse me.
Wait, shouldn't there be a negative somewhere? Didn't
Nope.
we say that down here?
That's complex numbers. So it's like complex numbers without the minus. Now, definition.
Oh yeah, you can't have minus in hyperbolic space.
Yeah. So, oh man. Well, I'm not sure what my notation is generally, but I'll use this for the moment. AX, let's say that is Z in the algebra such that Z inverse exists, meaning that Z inverse times Z is equal to the 1 in the algebra, right? So A with an upper X is the invertible elements of the algebra. and zd of A is going to be Z in the algebra such that there exists W not equal to 0 such that Z times W equal to 0, or W times Z equal to 0. Either there's a left or a right zero divisor. So ZD zero divisor. These are mutually exclusive camps. You cannot have an invertible algebra element which is also a zero divisor, and you can't have a zero divisor which is invertible. It leads to a contradiction pretty straight away. See, I'll show you the contradiction. Suppose you had a zero divisor, all right? You know, suppose X. You can't have a non-zero zero divisor. Now, I don't remember if I have included zero. In my current definition, zero's in the set of zero divisors. So, well, anyway, suppose X is a zero divisor. And let's, you know, and we have X times W equal to 0 for W not equal to 0, right? And then suppose X inverse exists. Then what? Then you have X inverse.
Well, it can't be 0 then.
And by the way, you can prove that any number times 0 is 0. That follows from the basic axioms of the algebra. But yeah, this then reduces to W equals to 0. But W was not equal to 0. Contradiction, right? So you cannot have a zero divisor which is also invertible.
Yeah, that wouldn't make sense. Like
And-
in any algebraic structure.
Right, and if you assumed that you had an invertible number, you could, and it was also a zero divisor, you could, I mean, you can get the contradiction starting either way. But anyway. So then, question, what are the invertible elements and what are the zero divisors of the hyperbolic numbers? Right? So this mapping I defined down here, right? This theorem, this map M, that's a mapping from the algebra to the regular representation of the algebra. This is a, how can I say this? Well, I'll just say this. It has m of x times y is equal to m of x, m of y. Also, m of 1 in the algebra, what's it give you? And now, so here, admittedly, I'm assuming that we're working with a basis.
Would it spit back out the identity?
It does, because you got, what you got? You see what you got? You got the identity, right?
Yeah.
And then the identity times the second thing, right? Which we're in our current context, I'm assuming that we're working with a standard basis, you know? So this, I mean, 1a is, I'm assuming that 1a is E1 here, and that a is equal to Rn in our current context. Again, I do have a generalization of this to work with basis, which are not standard basis and stuff in the notes. which we'll talk about some other day. But I'm trying to get to a kind of a big idea today before we go. All right, so, but yeah, this is the identity matrix.
Is that trivial or not? That should spit out the identity, or a function that has an identity.
No, that makes M very special. That makes this mapping, it's an isomorphism of vector spaces, in fact. But it's so much more than that because it preserves, it's also a isomorphism of algebras in the sense that it's taking, so the multiplication for M sub A is matrix multiplication. The multiplication for A is this star multiplication, this abstract multiplication. And this trades that abstract multiplication for matrix multiplication, which is super nice because, well...
Oh, I see now. Okay, yeah. It's spitting out the identity matrix. Just because you feed an identity doesn't mean it should spit out back the identity matrix.
No.
That's just super nice.
Yeah, but there are other things we can prove here, like the Z is an element of the invertible elements of A, implies, in fact, if and only if, the determinant of the matrix corresponding to Z is not equal to 0. Because that's the condition that a matrix be invertible. And that preservation of products property implies that the inverse of the element maps to the inverse matrix. The matrix, excuse me, the inverse of the matrix to which it maps is the representative matrix of the inverse element in the algebra. Like, let me write an equation. What I'm saying is that M of X inverse is equal to M of X inverse. This is inversion in the algebra. This is matrix inversion, which we have calculational techniques for.
Yeah.
So we already know what an arbitrary regular representation looks like, right? It has the form A, B, B, A. So apparently, A squared minus B squared, not equal to 0, is it. If that condition is met, the hyperbolic number is invertible. And also, if you want to characterize the 0 divisors, you just look for where it's 0. So the determinant of the regular representation being 0 gives you the 0 divisors.
Okay, so it'd be like A equal to 1, the 1, like everything's 1.
Ah, yeah. Oh, that would be an example, sure.
So that would be 1 plus J.
Let's see. Yes, 1 plus J. Very good.
Plus J,
Yeah, so for H, we have invertible things have the form A plus BJ, such that A squared minus B squared not equal to 0, which of course is entirely equivalent to A squared is not equal to B squared, right? Which is entirely equivalent to A not equal to plus or minus B. And that's often a convenient way to think about it. And the 0 divisors of A, H, are just of the form, well, A times 1 plus or minus J, such that A is a real number. Because this is what it looks like to have A equal to plus or minus B. So in fact, we can draw a picture. We can picture, here's A, here's B, right? Where are the 0 divisors? Well, 0 divisors are here and there. So there you go. These lines to the origin together are the 0 divisors of A. And as long as you stay away from those, everywhere else you're looking at invertible elements of A. Now, some people would say that 0 is not a zero divisor, because most interestingly, we think of non-zero zero divisors. Non-zero zero divisors are weird with respect to our regular experience in arithmetic. Like in Z mod 6, 2 times 3 being 0, despite the fact that 2 and 3 are neither 0, you know. Now, all of this said, you know how to find inverses in complex number systems, right?
Maybe. Did I learn that?
We do the conjugation trick.
Oh, yeah,
Yeah. That still works here.
Okay.
Like, you can define z bar equal to, let's say, x plus jy bar. It's x minus jy. And this conjugation of the hyperbolic numbers has, this satisfies certain properties, like z plus w bar is z bar plus w bar. But more interestingly, zw conjugate is the product of the conjugates. So if you have, if you want to have z inverse, so basically what you do, and well, z bar here is what? X squared minus y squared. So that better not be 0 if we're going to find the inverse, like we just learned, right? Okay, so if you have let's see here. So if we do, so we have, take this equation, right? And basically just, I mean, this is like formal what I'm doing, but just to show you where it comes from. So if I have z, oh curses, how to say this? It's not in my mind at the moment.
Okay.
There's a kind of a, anyway, here it is, 1 over z. Assuming it makes sense, it should be z bar over z bar. I mean, if z has the condition that x is not equal to plus or minus y, then z bar also has the condition.
Well, I mean, of course that makes sense because you can just cancel. I mean, you're just multiplying by z bar on both sides, or you're just multiplying by z bar, which is 1.
Well, I know, but this is technically formal nonsense because I haven't really developed the theory of division here or anything. You know, we talk about multiplication, but how does division work? Anyway, but this is, right?
Yes.
And, for what it's worth, z inverse, you could also calculate this way. Z inverse is it's the inverse of the M map of the matrix of Z inverted. So like the matrix of Z would be it's x, y, y, x, right? Mm-hmm. You got the inverse of a 2 by 2 matrix. We know that. Inverse of a 2 by 2 matrix is 1 over the determinant, which here is x squared minus y squared. Flip the diagonals. Nothing to flip here. Minus is on the off diagonal, right? And so what are you looking at? You're looking at, x minus jy over x squared minus y squared again.
Oh, yeah.
I'm assuming you can make sense of the inverse. What does the inverse map of M look like?
The inverse map of M?
Yeah, how's that work?
any standard matrix, don't you, you'd flip, I think, isn't that the one you flip the middle parts and negate the...
If I have M inverse of a matrix A, what's the formula for that? Assuming that A is in the regular representation.
So it is,
Maybe I should use
2 by 2 or
just
or
for generally speaking. Let me use
right.
I'll use R.
Um,
No, this is not matrix inverse. I'm talking about this map, the representation map. M maps from, M goes from the algebra to the representation of the algebra. I'm claiming that this is an invertible map, and you can write down the formula for the inverse very easily. So how do if M of V is this, and how do I get back from something like this to that? Like, what's the...
Oh, you would do... Well, it would just be... You would take out the J or V in this case, right?
Yeah, I mean, I think for this one,
And then it'd just be the matrix of E's.
M inverse of this should just be what? It should just be V, right? I mean...
Oh, yeah, because then you change V into the E's.
But what is V here? V is the...
Constant thing?
Well,
The ij.
no, I mean, what is V to this matrix? Like, V to this matrix is... It's column 1, right?
Yeah.
So, I mean, this is not especially exciting, but the inverse map to M is just the column map. It's column 1.
Okay.
It took me a while to see this, but once I saw it, I was just like, oh, duh. Now, that is assuming that the first basis element is the identity for the algebra.
Okay.
That's what I used here. You didn't notice it. I mean, I was kind of sneaky in my usage, but if you take this inverse matrix and you put the number inside the first column, you've got x over that and minus y over that, which translates back into x minus jy over that.
Yeah. And you said the inverse map is the column what? I just want to write that.
Oh, column, just picks off column 1. Yeah. Now, if you were working with a different basis, such that like the identity was if the identity for the algebra was like the kth basis element, then it would pick, you'd use the kth column.
Yeah.
What's worse, though, is if you were working with an algebra where you don't have the identity in your basis, then the formula for an M inverse is more complicated. All right?
Okay.
So this is the hyperbolic numbers.
Yeah.
And they're extremely interesting example. Many of my most interesting results happen in this example, just because it's so simple and quite nice.
So for your map up here, since those are hyperbolics, never mind, because you're not mapping in the real number sometimes. Okay, never mind.
Right. I mean, but these things, 1 plus j times 1 minus j, that's 1 plus j minus j squared.
2.
That's 1 minus 1, though. J squared is 1.
Oh, yeah, that's right. 0.
0. Non-zero, 0. So
Yeah.
yeah. Let me give you at least one example where the identity is not in the where we wouldn't make the identity a basis element.
Okay.
So this is, and you got to be really careful talking to algebraists. They have a habit of saying things that are isomorphic are the same. And if you have a different standard for what's the same, it's very confusing.
Yeah.
But here's another algebra. I'll call it B. And oftentimes I would just call it R cross R. It's the direct product algebra. The direct product algebra, it's the, here, I'll write out the formula over here. Here's the product AB times CD. So I also call this the Calculus 3 students are wrong product, because this is oftentimes what I see Calculus 3 students give me for the dot product AC comma BD. Now, I think technically, I think this is the so-called Hadamard product.
Well, wouldn't it be the dot product? Wouldn't it be plus?
Right, and it's not a vector.
Yeah.
You notice? So, I mean,
So
they shouldn't write that, right? Dot products is a scalar in Calc 3. But here, this defines the direct product algebra. And let me show you something. So if I have 1, 1 times AB, what do I get?
AB.
Uh-huh. Right, A comma B again, right? So that says that the 1 of B is in fact 1, 1. So I got to be careful. If I try to like just carelessly apply theorems I've worked out in the context that the identity element is one of the bases, one of the standard bases, I'd be up a creek here because it's not. The identity is 1, 1. And the M here, I can't use the theorem to figure out the regular representation.
Okay.
See, because 1 is not, I can't fall back on the theorem I just erased. So we'll go back to basic principles. We'll just work it out, right? So like, suppose you got a map F.
Oh, you're talking about the theorem that F E1 can be written as F of E1 times 2.
Right,
So on and so on.
right. No, we don't.
Yeah, you run into a problem fast.
Because we don't our basic principle that the identity is one of the basis elements is not met here. So just assume it's right, be linear. Let's see here. So we'd have F of 1, 0 times 1, 0, and like F of 1, 0 times 0, 1. I mean, we could do these things, right? So this would be it's like F of E1 times E2. This would be F of E1 times E1. Now this is just equal to what?
1.
This is F of 1, 0, right? So actually my first equation is just kind of dumb. Or is it dumb? Wait a minute. Why do I have E2 there? That's E1, E1. I'm a dummy. And so F of E1 times E1 is F of E1. But let's see here. This is what? What's this times that in the direct product algebra? 1 times 0.
Or 0, 0.
0, 0, right? And I'm assuming F is a linear map, okay? So F of 0 is 0. So, all right.
Wait, why is that E1, E1? It can't be both E1, E1. That wouldn't have to be E1, 0.
Oh, this one was supposed to E2. Sorry, that was 2. This is E2, E1. This is E2. All right, so the standard matrix of F looks like, let's say, how do you want to do it? A, B, C, D. I did sometimes I do A, B, C, D different. I did it this way this time. So like F of E1 is what? F of E1 is AB. F of E2 is CD. So this one equation we have is that F of E1, which is AB, right?
Mm-hmm.
F of E1 is equal to AB times E1, right? E1 was 1, 0. So what's this tell us? well, we can work this out, right? What's this work out to?
1, 0.
No, a times a,
Oh, yeah. A 0. Sorry.
a0, right? So we've got a0 equals ab. What's that tell us? It tells us a equals a. Good to know. Hooray. And what's b, though? B is
0.
0. All right. Now, we can play the same game with f of e2 times e1 and f of e2 times e2. Right? F of e2 times e1 is f of 0, which is 0. But that's also equal to f of e2 times e1, which is, in this case, cd times 0, well, times 1, 0. By the way, I didn't bother with the other equation because we already got what we needed from the first one. And maybe I can do the same here, you know. Maybe I should just, like, I don't know. What does this tell us?
C is equal to CD equals 0.
Yeah, I mean, this gives us c comma, this gives us c comma 0, right?
Yeah.
Which tells us that c is equal to 0, but it doesn't tell us anything about d. And
Why is C equal to 0 and DB equals 0?
well, this gives us c0, because c times 1 is c, d times 0 is 0.
And didn't we do the same thing up there?
That would have been analogous to the second line, which I didn't use. See, this would have been 0 is equal to, like, a b times 0, 1, which would have been 0b, which would have told us that b
B's already equal to 0.
b was 0,
Yeah.
which we knew from our other equation.
Okay.
So,
Okay.
I mean, there's some checks and balances here. Once we're done with it, if we've done it properly, we should have a description of the regular representation, which is the same dimension as the algebra. So, like, if you've got a bunch of parameters and you end up looking at it and you go, oh, it's, you know, n plus 2 dimensional, then that means you've missed 2 things.
Okay.
But here we're working 2-dimensional, so, like, it's probably going to be okay. So f of e2 is f of e2, but it's also f of e2 times e2, right? By the right linearity. So this gives us cd is cd times 0, 1, which is 0 d. So this tells us that d equals d, great, good to know, and c equals to 0. So, you know, after all this, just basically, I'm just facing the problem head on and, you know, working with the basis to determine what the matrix looks like.
Okay.
But after this, and there are other ways to do this calculation. This is just the way I did it. Like, you could just look at the right linearity condition and just with, like, A, B, C, D and work it out. That's how I did it to start with. But anyway, what we learn, let me erase all this, is that the regular representation here, the matrix representation of the direct product algebra, is matrices of the form A0, 0B, such that A and B are real. Ta-da! So the direct product algebra has kind of a boring matrix representation, right? It's just diagonal matrices. It's hard to get much simpler than that. So what's the inverse? When is AB invertible? It's going to be invertible. So you think about inverting this, right? I don't know, like however you want to think about this, but it's fairly clear that the inverse of A comma B should be A inverse comma B inverse, right? Because then if you multiply A inverse B inverse by AB, you'll get 1, 1, which is the identity here, right?
Yeah.
And you need the determinant of the regular representation for that to make, for, you know, just falling back on the theory that I talked about. So that's going to, this requires both A and B to be non-zero, right? Invertible elements of the direct product algebra are those for which both the x and the y component, both the first and second components of the vector are non-zero.
It is 6:10, by the way.
Yeah, we're good.
Okay.
I'm gonna be late for dinner because I think it's still. I'm gonna give this a little bit longer. We'll see. I'm gonna check again at 6:30, but I don't want to drive it. Do you want to drive in this? I don't want to drive.
I've driven in worse.
Ah.
I may not saying. I don't know. Oh, there it is. Okay, I didn't refresh.
Now.
It does that.
You can show. So there's another concept which I have not yet brought to bear here in terms of algebra, which is that if you have two algebras, right? If you have an algebra A with, say, multiplication star, and you have a multiplication, an algebra B with multiplication better looking star, kind of better looking star, like this, right? Then if you can define a mapping from one to the other, you can talk about a algebra isomorphism. So phi from A to B, you know, real vector space isomorphism. I'm trying to say real vectors, an isomorphism of real vector spaces, okay? So by that I just mean it's a linear map with linear inverse, right? Okay, so,
Linear map with linear inverse.
oh, wait a minute. Maybe the reason my fingers are numb is the chalk. Get most of the chalk on these three fingers. Huh, anyway, sorry.
Linear map with linear inverse.
Yeah. I mean, there's a theorem of linear algebra. If you have a linear map with an inverse, the inverse is necessarily linear. So it actually suffices to check linearity of the forward map and yowzers, bowsers. But here's the, I'm not done yet.
Yeah.
We also have preservation of the product. So psi of, let's say, x times y is equal to psi of x star psi of y. So you trade multiplication in A for corresponding multiplication of the images in B. So this is what defines a real algebra isomorphism. Okay. We've already had an example of this. The M map. In fact, you can prove that the M sub A, like this map M, that goes from A to MA, you can prove that if you make MA, if you think of MA as the B, where the multiplication is matrix multiplication, this defines an algebra which is isomorphic to the algebra originally thought of. All right? So, something interesting, you can prove that the direct product algebra is isomorphic to the hyperbolic numbers.
You can prove that the direct algebra is isomorphic.
You know, the H algebra and the B algebra on the board, they're isomorphic.
Okay.
And so to fix an algebra isomorphism, it suffices to like map the things which kind of generate them. So essentially, to guide my construction of psi, I want to have the number 1 map to the identity. So what's the identity? Well, the identity I'm going to go from, I'm mapping from H to B
The identity in H
is 1, right?
yeah.
So psi of 1 is of course, well, that is also, by the way, psi of 1, 0, right?
Yes.
But that's got to be equal to 1, 1.
I'm sorry.
You're fine. And then psi of j, which is of 0, 1, has to be equal to some element in the direct product algebra that behaves like j. And so you can find all of the j-like elements in the direct product algebra just by a little algebra exercise. Right? Like, let's do it. I had a couple students spend a whole semester just trying to basically come up with the analog of polar coordinates for this, where they use like a hyperbolic angle, and they have 4 different sectors, and it's complicated, but they have something that sort of resembles polar coordinates for this. We can look at that sometime, but so if we're looking for something in B such that like xy times xy is equal to 1, 1, right? That would be the element of the direct product algebra which behaves like j. So this gives you x squared, y squared equals to 1, 1, right?
So it could only be 1.
Well, you've got x squared equal to 1 and y squared equals to 1.
Well, you could say negative 1.
Right? You got plus or minus 1 for this, and you got plus or minus 1 for that, right?
Yeah.
So your choices are 1, 1, 1, minus 1, minus 1, 1, and also minus 1, minus 1. These two are out. You don't want those because those are actually the identity and minus the identity. So like those are not the right choices. But either, you could use either this or that as your quote-unquote j. And which choice you make will determine which, there's like more than one isomorphism, all right? So we could just make a choice, whichever one. Which one? We want to pick the first one? Let's pick the first one. 1 minus 1. And so notice that psi here is a mapping from R2 to R2.
Yeah.
So basically, this tells me that the standard matrix of psi, well, this is the first column, that's the second column. So like, there it is. 1, 1, 1, minus 1. And just to write the formula more fully, psi of, x plus jy is equal to 1, 1, 1, minus 1 times xy. So the formula straight up is x plus y, x minus y. And so there you go. That is the isomorphism of the hyperbolic numbers and the direct product algebra. One of two. If you made the other choice for the solution over here, that would have the effect of switching this plus and minus. Which, interestingly, would also have the effect of conjugation over here. Kind of funny.
Okay, I see what you're doing. Yeah.
So,
you get xy.
Yeah, there comes a place in time where I use this, because what this means is as we develop theorems and results, if we learn something about the direct product algebra, and we learn that a property is transferred by isomorphism, I can steal results from the direct product algebra and pipe them back over to the hyperbolic numbers, or vice versa.
Oh, okay.
And
Is that kind of how like the transforms work, like in differential equations?
in a sense, it's the similar kind of thinking. Change your problem from something hard to something easier. Solve the easier thing, work back, right?
Okay.
Now, beyond this, I have more examples. You can do things like, if you have two algebras, like A1 and A2 are two algebras,
Yeah.
then you can take like basically the Cartesian product of them, and that will give you a new algebra that looks like, x comma y, such that x is in A1, y is in A2. And if you do this, and you choose the appropriate sort of basis, what you'll find is that the matrix representation of A basically looks like the direct product of the matrix representation of A1 with matrix representation of A2. And by that I mean stuff of the form. What's that?
I was gonna let you finish. I was just saying, what did that plus with the circle mean? I remember that symbol.
It is like direct sum. So it's, let's see here. If I had like, if this was matrix A and I direct sum of matrix B, it looks like this.
Okay.
So for an example of this, getting too bogged, if I make my algebra the direct product of, say, the complex numbers and the hyperbolic numbers, that would give me a four-dimensional algebra. And with respect to the basis that's sort of most natural, just string things in order, the matrix has the matrices of these would have the form something like A B minus BA C D D C zeros. So the regular representation of this is something like that, for example.
Is that why the space is n cubed?
N cubed.
N squared. Like, you remember when you said that, like, these things live in a space that's typically
N squared dimensional. Oh, it's just because the if we're thinking about matrices being n by n,
yeah.
the basis for the matrices are the EIJ things, like the matrices that have 1 in one entry and 0 elsewhere, and they're just n squared of those.
Oh, okay. So this is not an example of that?
No, I suppose this is a four-dimensional algebra, and in the 16-dimensional space of all possible 4x4 matrices, this is a special four-dimensional subspace of that.
Okay.
There's 12 other dimensions not used by these guys,
Okay.
which I'd like to talk about, actually. So in this space, the identity for this one, like what does 1a look like in this example? It would look something like 1 comma 1. But you've got to understand that that's the 1 of complex numbers,
Yeah.
and that's the 1 of hyperbolic numbers.
Oh, okay. So the one of complex is still the identity
Yeah.
under multiplication.
If I'm working with pairs of complex and hyperbolic numbers, then the identity here is 1, 1. So this is another example where I can't use the theorem where the first basis element is the identity.
Yeah.
So I do look at such examples. It's just like, you got to be wary of them. All right, so now we have, there are other, you have talked about the quaternions before?
No.
Oh, you've never seen quaternions?
Mm-mm.
All right. We'll talk about the quaternions another day. That is something that deserves a solid like half hour of our time. But that's that is the most interesting example of a non-commutative algebra. It's a four-dimensional non-commutative algebra where every non-zero element has a multiplicative inverse.
Okay.
So it's almost a field. A field is every non-zero element has a multiplicative inverse, and it's a commutative space. So like quaternions are not commutative,
Yeah.
but they're sometimes called a skew field because they're almost a field. They just lack commutativity. So quaternions are a very quirky and interesting example we should talk more about. But That's another example of an algebra, four-dimensional algebra. There's also some things called matrix algebras, which will play an important role in our larger discussion. We'll introduce those in a future meeting. But so now that we've talked a lot about algebra, I want to talk at least a little bit about calculus today.
Okay.
I want to share with you the central definition that guides what we do. So here it is. A function, f, from the algebra to the algebra is a differentiable at a point P and A if f is real differentiable and the differential of f at the point P from A to A is right alinear. Now, I think in future meetings, I may cut this a little bit more finely. Trying to remember here. Yeah, I mean, if you look at my definition 5.4, it looks a little different than this, but this is essentially, I mean, you can contrast to definition 5.4. Basically, in definition 5.4, I give you a limit whose, I assume, in definition 5.4, I write a limit, and I say that that limit has to exist, all right? Well, the existence of that limit is tantamount to the function being real differentiable. So it's not a big deal. But all right, so notice here, I know we've been in differential geometry for a while, so we have gotten in the habit of making the differential and act on abstract vectors, which are operators. We no longer do that here. Here, this is more like calculus 3 or a lot of other analysis where if we're working with a vector space, since we have a global tangent space which we can identify with the space itself, we just make the the differential still acts on the space is the thing here.
Yeah. Okay. So we can say the f of p acting on d, or what we used to do. I know what you're talking about.
So here we have the condition that df p of v times w is dfp v times w. That is right alinearity. All right? So let's just focus here. Context. Let's let v1 equal to the identity again, and then v2, vn, basis for Rn, which I'm going to think of as being A. All right. Again, this specialization is not necessary. It's just convenient for saying the most interesting things. Just checking on my mic. It's been a few days since I charged batteries. So let's look at what this means. So what is the basis? What does the matrix of the differential look like? We've talked about that a fair amount this semester, right? The matrix of the differential is the Jacobian matrix of f, right? And that is like partial f, partial x1, partial f, partial x2, partial f, partial xn.